Hello and welcome to today's lecture in the course for Secure Systems Engineering. So, in today's video lecture, we will be looking at Intel's SGX or software guard extensions. So, this is part of a series of videos on trusted execution environments. We looked at the ARM TrustZone in the previous video and the ARM TrustZone also creates a trusted execution environment, but as we will see in today's video about SGX, the entire way of doing it would be much different. Therefore, from some perspective, the guarantees obtained and the security obtained by SGX would be much more preferred for server type of machines, while ARM's TrustZone is more suited for the embedded platforms and so on. When we actually normally look at a machine or a system, we see that there are multiple layers of hardware, there are VMs, operating systems, and above that the application. Now, the trust surface or the attack surface in this particular scenario is this entire scheme. So, what we mean by this is that if, let us say, the application has something secret, let us say a secret key, then this particular boxed area is the region which you actually assume to be trusted in order to keep that key secure. For instance, if there is a malware in the application, then that particular malware could steal that secret key. Similarly, if a malware now attacks the operating system or the VM, then the key which is present in the application can be compromised. In a similar way, a malware or a Trojan present in the hardware could steal the secret key in the application. So, what we see over here is that in order to assume or to keep something secret in a normal system, we would require a huge amount of assumptions that all the underlying hardware, the system software comprising of the virtual machines, managers and the operating system are all trusted. Now, what SGX actually helps us do is that it reduces the potential attack surface. So, this is how a SGX enabled computer system would look like, and over here let us say that we still have an application, and this application has a secret key. Now, with SGX, this secret key would only require that portions in the application which is boxed in this red dotted line, and portions in the hardware is actually trusted. So, you could still have an untrusted operating system, untrusted virtual machine managers and so on, but what is required to keep the key secret is just that the hardware, a portion of the hardware is trusted along with small areas of the application. So, what we achieve by this is that we are drastically reducing the attack surface. Now, if you compare the normal mode of operation versus the SGX enabled mode of operation, we see that an attacker could have attacked either the application, OS, virtual machine or the hardware in order to gain access to that secret key, while in the SGX enabled hardware, the attacker would have to target small regions in the hardware or small portions of code in the application in order to achieve or in order to gain access to the secret key. So, let us look into more details about how SGX actually works. So, let us say that this is our process space. So, as we have seen before, the process space has the code, that is the application code, application data comprising of stacks, heaps and so on, and higher in the typical address space of a process is where the operating system resides. Now, what SGX permits us to do is to have enclaves in this address space. So, what we see over here is that within this entire address space of the process, there is one region which is called the enclave, which provides the necessary sandbox to achieve the trusted execution environment. So, within this particular enclave, you could have some regular code stack and heap. So, we call this as the enclave code, enclave stack and the enclave heap, and you would have some management data such as the entry table and TCS, which is a thread control structure. So, all of this can be present in an enclave. Now, what makes this enclave unique is that any code, any function or anything which is executing outside this enclave, for example, in this green region over here, will not be able to access any code or data present within the enclave. So, for example, a code present over here cannot directly call a function present in the enclave code. Similarly, code present outside the enclave will not be able to directly invoke data or access data in the stack or in the heap present in the enclave. However, the vice versa is true. Now, if you are running code within the enclave, this particular code will be able to access the stack and heap present in the enclave, as well as all the other application data and code present outside the enclave as well. So, what the enclave actually permits us to do is that it is able to create a closed sandbox through which you could get confidentiality and integrity. So, what we mean by confidentiality is that the code and data present inside the enclave is kept confidential with respect to anything or any code or anything else outside the enclave. So, typically this is achieved by multiple ways. For example, there is encryption which is done, and we will see more about it later in the video, and also there is a special memory management units present in the hardware, which creates an environment so that confidentiality of the code and data in the enclave is achieved. In a similar way, we also achieve integrity of the code and data that is present within the enclave. So, what we mean by this is that any code and data cannot be tampered or modified by an external party. So, this is typically done again using special purpose hardware or special purpose memory management units present in the hardware, as well as a lot of cryptographic algorithms to ensure that the data is not tampered with. Now, one thing what the SGX in the Intel processors also achieve is that it ensures that when data goes outside the processor, that is, if data or code from the enclave is going in or out of the processor, it has provisions to ensure that no attacker could actually monitor the various buses or snoop at the DRAM present on the system, and would be able to actually identify what the code and data actually is, or this is achieved by having memory encryption. So, essentially any data which is to be executed from the enclave is going to be stored in the RAM in an encrypted state. Now, when this data is moved from the RAM to the processor, it gets decrypted within the processor. So, thus if there is a snooping done on the data bus, or there is actually snooping within the DRAM, then what would happen is that the attacker would only see encrypted code, and the sensitive data and information is still kept secret. So, let us see how these things actually work internally. So, SGX is quite a complicated mechanism to achieve this trusted execution environment, and we will just see a very brief overview in this lecture about how these things would work. So, to start off with, what happens in an SGX enabled Intel processor is that some portion of the RAM is marked as PRM. So, this is known as a processor related memory. So, this area, let us say from some address say A to some address B, is marked by the BIOS as a processor related memory. So, what this means is that the operating system or any applications running over the processor would not directly be able to access the memory in the PRM. Also, the speciality of this PRM region of memory is that no external device, like no external master device such as network cards or graphic engines and so on, would be able to read or write data to this PRM. Essentially, going a bit more technical, the DMA accesses to this particular region of memory, that is the PRM region of memory, is disabled. So, what this means from an operating system is that this region, the PRM region, is identified by the OS as non-existent memory. So, it means that there is a hole in the entire memory RAMs of the processor, or rather the operating system sees this PRM as a hole in the memory region, and therefore would not allocate any memory or any other data or try to store any other data in this particular region. From this, what we actually achieve is that we have this region of memory which is completely in the control of the hardware. So, the hardware could use this region of memory to create enclaves, manage the various enclaves, manage the memory, who accesses these enclaves, the read, write, execute permissions for these enclaves, and so on. So, internally what happens with the PRM is that it is divided into several EPCs or enclave page caches. So, each of these page caches which is shown over here is of 4 kilobytes. So, these page caches are used to actually store the enclaves of the various applications present in the program, and also there is some management related information which is stored in a special region known as the EPCM, or which expands to EPC microarchitecture. So, the way it works is that we have multiple processes present in the system. Each process has its own virtual address or space, and within this virtual address space each process could have its own enclave. So, per process you could have one or more enclaves, or you could also have a process without any enclaves as well. So, therefore, you would now have a mapping for these enclave region within the virtual address space to this PRM region in the RAM. So, we have the memory management unit which converts the virtual memory to the physical memory address, and the operating system would ensure that addresses from these enclave gets mapped to physical pages within the PRM present in the RAM. So, therefore, you could actually have multiple processes like this, each of them having their own enclaves, but all of these processes would map to the same region within the RAM, that is the PRM region. So, let us look at the EPCM, which is the acronym for Enclave Page Cache Map. So, this EPCM is further divided into various sub-regions, and we have one entry for each EPC. So, for example, if there is say 1024 EPC regions, each of 4 kilobytes, then there would be 1024 regions in the EPCM. One region is associated with the corresponding EPC. So, essentially this EPCM is used by the hardware for access control. It stores various information related to the corresponding EPC. So, for example, this particular EPC would have a corresponding EPCM entry which stores aspects such as the validity or of that particular EPC, the read, write, execute permissions for this EPC. For example, if there is code present over here, you would have that particular code as executable and not writable. It also stores the type of page and the virtual address range for that particular EPC. So, in some sense this EPCM is somewhat similar to the page tables which are generally used in systems. The only difference is that most of the page tables are managed by the operating system, while with the SGX the EPCM contents is completely managed by the hardware. So, if we actually go back to this slide and see that there is now a conversion from the virtual address space for the enclave to the corresponding physical address space in the PRM. Now, as we will see later, there are actually two translations that are involved. One is by the standard memory management unit and the page directory and page tables which are maintained by the operating system. So, this region would then would essentially convert the virtual address to the corresponding physical address. A second set of validity checks is done by the hardware using the EPCM which is present in the PRM. So, this would permit a scenario where the operating system is not trusted, and the additional checks done by the hardware would ensure that the enclave code and data is kept safe even when the operating system is untrusted. Now, another related data structure which is present in the PRM is known as the SECS, or the SGX Enclave Control Store. Now, for each enclave there is one SECS, so it is of 4 kilobytes, and what we mean by this is, suppose there are, let us say, 10 processes running in the system and each process has one enclave, then there would be 10 SECS structures present in the PRM. So, this SECS structure contains global and metadata about that particular enclave. It is used for various reasons such as to ensure the integrity of the code and data present in the enclave, and it is also used for mapping information to the various enclave regions. So, as we mentioned, one of the distinctive features of the SGX mechanism compared to the ARM TrustZone is that SGX supports encrypted memory. So, if we look at this, so if we consider this as our processor with the multiple cores and so on, and we assume that this is a hardware enabled processor, then what happens is that any data which is actually sent out of the processor or received from the processor is in an encrypted state. When this encrypted data enters into the processor, then a very fast decryption engine would decrypt it to get the plain text data. So, what this means is that any data leaving the processor would be encrypted, while any data read into the processor which is present in the enclave would be decrypted. So, this way, if we have an attacker who is trying to snoop into the system memory, the DRAM memory for instance, or try to snoop into the various buses present in the processor, then the attacker would only be able to view the encrypted data. So, this ensures confidentiality of the enclave region as well as integrity of the data. So, for example, if an attacker tries to modify this data on this bus, checks would be done in the processor to identify that the data has been modified and would throw an exception. So, recollect this slide where we actually discussed that the enclave region is essentially protected from the various other parts of the process as well as the operating system. But however, when executing within the enclave region, that is, you have a function within the enclave region, this particular data could access anything in the user space of that particular process. So, this leaves us 4 different alternatives. So, let us say the first is when you are in the code outside the enclave, that is, you are executing in normal mode outside the enclave, and you are trying to access the data present outside the enclave. So, this should be permitted. The second is when you are executing code outside the enclave, but try to access or execute code which is present inside the enclave. So, this should not be permitted. The 2 other cases are when you are actually running in the enclave mode and you are trying to access data within the enclave or trying to access data which is outside the enclave. So, both of these should be permitted by the processor. So, let us see how this is managed by the memory management units and the SGX units present in the system. So, we look at this particular flow chart which shows how memory accesses are done in an SGX enclave system. So, part of this is done by the operating system and the traditional page tables and page directories which are present. The remaining part is done by the hardware, especially the SGX aspects of the hardware. So, let us consider the case where we have code present outside the enclave and it is making a memory access to data which is also present outside the enclave. So, we will follow the flow chart and see that this should be permitted and only the traditional page tables and page walk mechanisms would work. So, we have a memory access that is which is initiated. We set the enclave access to 0. We check whether it is an enclave mode. In this particular case, it is no. So, we skip these steps and we go to this place. Then we perform a traditional page walk and page table, page walk using the page directories and page tables, and therefore, we will be able to convert the virtual address of that data to the corresponding physical address. Now, the next step is this an enclave access? So, since the data is outside the enclave, so therefore, no. Then we check whether the physical address is in the EPC. In this case, since the data is not in the enclave, the data is outside the enclave, therefore, this case is also no, and finally, we allow the access. So, let us see another scenario where you have code present outside the enclave trying to access data which is present inside the enclave. So, we will follow this again. We will set enclave access to 0, then is it in enclave mode? So, it is no. So, we go here, perform the traditional page directly page table walk and obtain the corresponding physical address and check whether it is an enclave access. So, enclave access is still set to 0. So, it is no again, and then we check whether the physical address is in the EPC. In this case, it is yes, and what we do is that we replace the physical address with some non-existent memory address. Essentially, we are going to actually fill in some garbage and permit the access. So, what is going to happen over here is that such a memory access would complete, but what the program would see is some garbage value and not the actual value corresponding to that memory location present inside the enclave. We will also look at a third aspect where you are running in the enclave mode and trying to access data which is outside the enclave. So, we will follow this again. We set the enclave access to 0 as usual. We are running in enclave mode. So, this is yes. The access to address in enclave address space which is no. So, we come here, we perform the traditional page table walk and obtain the corresponding physical address. Then we check whether it is an enclave access equal to 1, no. So, because enclave access is still 0. So, we come here and we see that there is a check for physical address in EPC. In this case is no, because we are in the enclave mode, but trying to access data which is outside the enclave, and therefore, the access is permitted. We will also look at the final case where we have a code present in the enclave, that is you are running in the enclave mode and you are trying to access data which is also in the enclave. So, as usual we set the enclave access to 0, the enclave mode is yes. So, we actually come here, is the access to address in the enclave address space, this is yes. So, set enclave access to 1, we go here, perform the traditional page table page walk thing, which will actually convert the virtual address to the corresponding physical address. Then we look at the enclave access equal to 1. So, in this case the enclave access is indeed 1. So, we come to this part of the flow and check whether the physical address is in the EPC, yes. Now, over here we is the part where we actually look into the EPCM, check the various permissions and so on, and ensure that this particular EPC where is going to be accessed has indeed the right permissions to permit that particular access. If these permissions are successful, then you allow this particular access, else we will create a signal fault. In this video, we had a brief introduction to Intel SGX. In the next video, we will look at how more from a software perspective and see how applications are written, how the SGX mode is used, and how data can be transferred from a normal mode outside the enclave into the enclave and get the result and so on. Thank you.